7.7 Euler's method. This is a numerical way for you to approximate the solution to a differential equation. So what's happening is that they're using the equation of the tangent line to move to a point that is very close to the point that the tangent line is centered at. So if you are centering a tangent line at the point P sub 0, then this would be your tangent line, something like that. You're going to move, like 0.1 or 0.01 or 0.05 away and calculate that on your tangent line. Then from that point, create another equation of a tangent line and then move, 0.1, 0.01, a delta x away. And then that will give you this one. You're going to create a new equation of a tangent line, move again delta x away, and create a new equation of a tangent line, and so on and so forth. So you are basically sketching out the approximate shape of the curve by doing that. And of course, if your curve is concave down, it's going to be, all of your values are going to be over estimates. And if it's concave up, since your tangent line would be below it, all your values, your approximations are going to be under estimates. So that is basically how we're doing this numerical method. So let's go ahead and explore this. When you do this, you're given a delta x that they want you to move, you're given a point that they want you to start at, and you're given the slope, the differential equation. Okay, so our differential equation for this exploration is y, dy dx equals y. Y of 0 is 1, so that means my initial point is the point 0, 1. Since my slope is y, then whatever my y value is, that is going to be the slope. So this one's kind of easy to calculate that slope. It's not always that easy. So we've got the tangent line then, and that would be your y equals, you've got your slope of 1 times x minus your x1, which would be 0, and then plus your y, and my y is 1. And now this equation of this tangent line that is created giving your initial point and your initial slope, you're now going to move to your next x value. Okay, so from you would be adding your 0 plus your delta x of 0.1. So this is going to be 0 plus 0.1, which would be 0.1. And then you want to put that x value into this equation. Remember, you're finding your new x value on this tangent line. So you're putting it in here for your for this x value. Okay, so you're putting it in there. So to calculate that, you would get 1.1. And this now is your new point, your 0.1 comma 1.1. So this is your new x, this is your new y, so this would be your slope because your slope is y for this particular problem. Now you create the equation of the tangent line, so your slope is 1.1 times x minus 0.1 and then plus 1.1. And so your new x value would be 0.2, and you're putting that in to the x and finding that equation, that value, that y value, you're finding the y value on that tangent line. So your new y value is 1.21. So then you've got 0.2 and you've got 1.21. And then since your slope is your y, there's your 1.21. Y equals, this is going to be your m times x minus x1 plus y1. And then you increase your x and then put that value in for your x here. And again, you can keep this up. You could pause the video at this point and just finish these just to see if you can do it and understand what you're doing without me showing you the whole thing. And I'm just going to keep going here just because I'm going to have to get this done. But I do encourage you to just pause this video and go ahead and try and finish this one on your own, so that you can kind of get the feel for what you're doing, and it makes you kind of think about, okay, what am I writing? What am I calculating? Because I'm going through this pretty quickly, and I don't want you, to just go through this and then not really understand what you're doing. But as I'm increasing here, you can see that whatever I get over on the right, I'm just rewriting it over on the left and then calculating my slope, although there wasn't much of a calculation for this particular problem because I didn't really have to do anything. It was just my y value to find my slope, where on other problems it's not going to be that easy. And then putting my 0.5 in to calculate my y value estimate at 0.5. And here's our last equation of our tangent. Our next one for x would be 0.6, and if I put that 0.6 into this equation, I should get 1.771561. So normally on a problem like this, it's not an exploration. It won't be asked like that. It will be asked like estimate, y of 0.5 or y of 0.6, let's say, because we did take it all the way to 0.6. Oops, I meant to erase that. There we go. Estimate y of 0.6 using, the differential equation dy dx equals y, and delta x of 0.1, and starting at the point, 0, 1. So it would ask something like that. And I know that this is a little confusing because our y values of our tangent are also y, but this y that I'm talking about right here would be the y of your answer to your differential equation. So it'd be your original function with your differential equation if we integrated it. So with that y, it's like, give me an estimate. So therefore we would say, for our answer to one like that, we would say that our y of 0.6 is approximately 1.771561 based on what we just did there. And we started at 0, 1, and we went by 0.1 increments to get to 0.6. So you can see that, over here, these are your estimates for points. And then we just brought that point around to the left on the next row. And if we kept going, that's what we would have done. So that leads us to example number 1. What I don't like about example number 1, about doing things here, is that they're using a different table. And so I thought it might be a good idea to kind of show you everything based on the table that we were just using. So I was going to try and come over here and kind of try and show you, because this gets confusing if you don't understand the method yet. So it says, show that Euler's method for dy dx equals 0.5 times x plus y, starting at 0.2, 1.11, and using 2 steps with delta x equals 0.05, gives us y approximately equal to 1.1775 when x equals 0.3. So our initial point that we're starting at is the point 0.2, 1.11. And so if we were going to find our dy dx, and that would be our next thing, our dy dx for that point is going to be the number 0.5 times 0.2 plus 1.11. Okay, that's going to give us our dy dx. And if we put that in our calculator, we should get 0.655. And so that's our slope. Okay, and we can create our equation of our tangent line, y equals 0.655 times x minus 0.2 plus 1.11. Okay, so that's the equation that we're going to use when we move our increment up by 1. So our x plus our delta x is going to be 0.2 plus 0.05. So it's going to be 0.2 plus 0.05 because that's our new delta x for this particular problem. So it's going to be 0.25. And then we're going to put this x value into this equation. Okay, so you're putting your next x value into your prior point's equation to find your new y value. Okay, so we would say that our y equals 0.655 times 0.25 minus 0.2 plus 1.11. So that is our dy dx times, look what happens when you put your x value in and you've only moved it by one increment. You can see that this is your dy dx times your delta x plus your previous y value. Okay, so that I'm going to call that y1, or actually for this one it'd be y sub 0, right? Because if we said that this is our initial x and our initial y, sorry, that was a 0. And so you can see how this is going to give me my y of 0.25. So that's going to be my new y. So this is going to be my new y value, okay? And so when I do that calculation here, I should get my 1.14275. I think that's what that's what I got. So how does this relate? Because this is exactly what we did in the exploration, okay? Everything we just did here. So how does this relate to what they're asking us to do here? Well, this dy, this is our dy dx times delta x. Okay, so this is our 0.655 times 0.05. Okay, so this is our 0.655 times 0.05. And then I add this value, 1.1, plus my dy to get my new y. So it's basically what we're doing right here in this right here. That is our dy dx times our delta x plus our y value of the previous point to get the y value of the next point. Okay, so this is going to be our 1.14275. And then we would say, okay, well, our new x value, we're moving up by 0.05, and then this is our, sorry, I'm kind of shaky here, our y value that goes, that's our new point. So if we were doing it like the old way, we'd say, okay, for this point, 0.25, comma, sorry about that, comma 1.14275, we've got y equals, and then we would have to calculate the slope. So our slope would be our dy dx, I'm going to move this over a little bit, our dy dx would be, for this particular problem, 0.5 times 0.25 plus 1.14275, and our dy dx then would be 0.696375. And so 0.696375 times this would be our x minus 0.25. Sorry, I'm running out of space here. Plus our y value of 1.14275. So this is the equation of our tangent line for the second part of the problem. But what they're doing here is, and then of course we would increase our x value. So our x plus our delta x is going to be our 0.25 plus 0.05. So 0.25 plus 0.05 is our 0.3. So our y at 0.3 approximation is going to be found by taking and putting that into this equation of our tangent line at the previous point. And so our y of 0.3 is going to be approximately equal to, notice that I've got my dy dx, and that this ends up being times delta x, which is what they're asking you to do at that, our dy dx times our delta x is what they're asking you to put into this problem right here. And so, and then add on your y value. And so I got 1.17756.875 for my new y value. And if you were you would put 0.69637.5 times 0.05 there, and then you would have your 1.17756.875. And see, this is your approximation at your 0.3. And so they're asking you, show that Euler's method starting at 0.2 comma 1.11 and using two steps with delta x equal to 0.05 gives you that y value. And if we would have gone to the next one, 1.17756.875, that would have been the y value. You would have seen that it was approximately equal to, they truncated it instead of rounding. They just truncated it at the 10 thousandths place, but that's fine. Okay, so that is us showing that Euler's method gives you that value when x is 0.3. Okay, so that leads us to our second example. And now they're, listing even a different, listing it even a different way. So I'm going to try and walk you through that. They want us to start at 0, 2. So that's our initial, so the way they did this one is they're like, okay, we're starting at, x equals 0, y equals 2. We don't have a previous here because this is our first point. And so that's the point 0, 2. So for this one, we would go and we would say, okay, if our delta x is 0.1, we're going to add 0.1 to x. So that's going to be 0 plus 0.1, which is 0.1. And then we're going to find our delta y using our previous is y prime. So the y prime with the previous point is negative 3x squared times y. So therefore, we've got our dy dx with our previous point is negative 3 0 squared times 2. And so this is just 0. So for that one, your delta y is going to be 0 times 0.1, which is 0. And so your new y value is going to be 2 plus 0, because remember, this new y value is going to be your y plus your delta y. That's what you'll be, so 0 plus 2, these two added together, right? These two added together gives you that. And so your new point, though, is 0.1 comma 2. And then you increase by 0.1. And then your delta y for this next one, you've got to find your dy dx for the previous point. So it's going to be negative 3 times 0.1 squared times 2. So that one is going to give you negative 0.06. So this is negative 0.06 times 0.1. And that one's going to give you negative 0.006 for your delta y. And then you add those two together. And since it's negative, it will give you 1.994. And so now your new point is 0.2, comma, 1.994. And then 0.3. Delta y equals. And so over here, I'm finding my dy dx, negative 3 times 0.3 squared times our y value of 1.994. And that one's going to give us negative 0.23928. Oops, sorry. That should have been 0.2 squared. Sorry about that. And because we're using the previous point, sorry about that. I accidentally put 0.3 instead of 0.2. And so this one is going to be negative 0.23928 times 0.1, giving us a value of negative 0.0233928 for our delta y. So when I add that number with 1.994, I get 1.970072. And then my new point is 0.3, comma, 1.970072. That's my new point. And of course I come here, but to calculate that, I'm using the previous point. So my dy dx, negative 3 times 0.3 squared times 1.970072. That's a point. And that should give me negative 0.53191944. And so when I take that times 0.1, that gives me for this value negative 0.05311919. That's a 1, 4, 4. And that's a 4, sorry. And then add that to my 1.970072, I get 1.91688056, and then my new point, 0.4, comma, 1.91688056. And so they wanted us to approximate 4 points on the solution curve. So my final answer, and I know this is very messy and I'm so sorry, but my final answer are those 4 points. I'm going to erase this little guy right here because he was part of that other problem. But those are the 4 points that they were asking us to approximate right there. Approximate 4 points on the solution curve. So these are the approximate 4 points. If we graphed those 4 points, we would see like the little shape of the estimated shape of our function that is the solution to this differential equation. Okay, so the solution to that differential equation, when I say the solution to it, if I separated it, right? If I said dy equals negative 3x squared y dx, and then I divided by y on both sides, giving me 1 over y dy equals negative 3x squared dx, and I integrated both sides. Whatever function I get, that solution, that's what the solution to that differential equation is. You separate it and you integrate both sides. That's sometimes these are impossible to take the integral of. And so you want to have points like this so that you can actually move along the curve and find out what that original function is. At least have a general idea of what the function is. All right, so that moves us to page 30 in our notes. And this is talking about how accurate Euler's method is. So it says the error in using Euler's method is exact value minus approximate value. So if the number of steps used is n, the error is approximately proportional to 1 over n. So for this example, it says compare the tables below. Each represents the specific solution to the differential equation dy dx equals y, where y of 0 is 1, with delta x equal to 0.1. Euler's method is an approximation of the particular solution. And so there is your Euler's method solution, starting with 0, 1, moving by 0.1. You would get all of those values. And here are the exact values of the particular solution, y equals e to the x. And you can see how accurate they are. Okay, so, of course, 0, 1, 0, 1. 0.1 is 1.1, and then this one is 1.10517, right? So 0.2, 1.21. This one is 1.2, so it's exact for 10 to the negative 1. 0.3, exact for 10 to the negative 1. 0.4, exact for 10 to the negative 1. Less than 10 to the negative 1. 0.5, exact for less than 10 to the negative 1. So that's just, that example just kind of shows you that, what you have here. And then for part A, it says the graph at the right illustrates the particular solution as it compares to the Euler approximation. Why do the approximate values underestimate the actual values? So hopefully you're thinking about that, and I think you probably all know the answer to that. We've done this before. I'm going to write that each tangent line will lie below the curve. The solution curve y equals e to the x is concave up. And we use these tangent lines to obtain our approximations. They all lie below the curve and are thus underestimates of the actual values. And then part B, complete the table at the right, comparing the difference between exact value minus approximate value. And why are the approximations getting better or worse? Are the approximations getting better or worse? Why? Okay. So if I take our 1 minus 1 here, I get 0, because I'm looking up at that original table and I'm taking the exact minus the approximation. So for 1.10517 minus 1.1, I'm going to get 0.00517. For the next one, 1.2214 minus 1.21, I get 0.0114. For 0.3, I get 1.3498 minus 1.331. I get 0.0188. For the next one at 0.4, 1.4918 minus 1.4641. I get 0.0277. For the last one, 1.6487 minus 1.61051. And I get 0.03819. And you can see that they are getting worse. And the reasoning would be, we know that e to the x rises very quickly. So I would say they are getting worse. Because y equals e to the x starts to grow quickly. And we're using linears for the approximations. So very quickly. Okay, what can be changed to make the Euler solution curve more accurate? We could make delta x smaller, and then we would be moving by smaller increments, and it would make our approximation better. So now, this last page of your notes shows you a way to see a slope field. Sorry, I was trying to think of the word. It shows you a slope field, and it shows you the solution to a differential equation. So it shows you how to do it on the Inspire CAS, which I have my teacher one, and the one that I have on the computer here is an Inspire CAS. And it actually is a pretty cool little application. I don't think your TI-84 does this. If somebody wants to investigate that, if you can figure out how to see that on the 84 and email me, that would be lovely. And if not, I'm going to try and see if I can show you this online and somehow make a video. Right now, not sure how to do that. So, but thank you so much, and this is the end of our Euler's method. Hopefully you'll be able to do some of your homework. I know there's some good book problems that go with this, but I'm not going to give them to you. I'm going to let you go ahead and look at your homework for that I've given you so